Okay, hi everybody. Here come the radians. Okay, so hopefully you watched those two videos. The short one's really nice. And I'm gonna emulate what they said there and actually use some of the terminology that they use. Not terminology, just the ideas. And I'm doing this with the CAT classes as well. And really want to remember that it doesn't matter the size of the circle when we convert or describe what a radian is. So let's pretend on the second video, I think they had a real weird length for radius. It was like 3.2 something or other. So it doesn't really matter. Let's say this is like 1 foot. I'll say 2 feet. So pretend that's 2 feet long there for a radius. Well, from the video, if I get an arc length that seems to be right around 2 feet, and I tried to kind of draw that the same length as this, but it's just curved, so it lays curved on there. And this is 2 feet long. Then what you have when you enclose this angle, and this is the angle from these are the two rays, then this by definition is 1 radian. When the arc length cut by these two rays is equal to the radius itself. So it's just another way of interpreting an angle displacement. Actually, what's great about radians is now you're more ready to deal with angle measures that translate to actually real world measures, because a radian is created from real world measures. Right? That's the idea. So if someone's thinking, what is this? Why radians? What is going on? Well, I just told you that's the reason. So radians actually open up a whole new world of being able to deal with direct measures of real world sides to angular displacement in a real world measurement. Right? And then, of course, as the video kept going, this is like another 2 feet. So this is another radian, the 1 radian. But this angle measure from here to here is 2 radians, right? And that's the idea as we keep going. You notice from the video, they kept going. Right around 3 radians was like right here. And we could do this by measuring. We could actually get a tape measure, maybe a tape measure that bends, and then we could, measure 2 feet again here. And this is where you would be at the circle. All right, so this is another radian. This whole measure from here to here is 3 radians. So on and so on and so forth. And it's positive, just like with degrees, when we go counterclockwise, radians will be expressed both in positives and negatives. It's no coincidence that this is 3 radians and pi is equal to 3.14, a complete half circle. And you can look at the video again. The second video explains this, comparing it to area of a circle, or circumference, sorry, not area, circumference of a circle. And in any circle, this is what would end up happening, the rotationally. And then, yeah, a full circle is 2 pi. They keep going and they do another radian. I don't feel like changing colors. That's 4 radians. This is approximately about, I don't know if I go past that or not. 5 radians, I think it might. And then 6 radians almost does a complete all the way around. But really what it is 6.28. I do love what the first person did too, or the second one. I think the second one talked about 1 radian equals approximately 57.2-ish degrees. I'm actually going to show that using the second video, how to convert degrees to radians. Okay, so really that's what it is. I remember when I first started teaching, I threw radians out there. I don't quite understand them. Where's it coming from? And didn't quite grasp it. Obviously now I do. And it doesn't matter. It doesn't matter what this, circles are all proportional. If I make this go gigantic and pull this circle and make it really large and turn it into a radius of like 25 feet, let's say. Well, then proportionally this circle, this arc length is 25 feet, and it would still land in this position where it would cut through this. So radians are all uniform in all circles, no matter what size or shape. Just like degrees. If I just make the triangle really big, it still wouldn't change what this angle measure is if I just make a proportional relationship, similar triangles kind of situation. So there's your radian. So from the other video, we got some conversions that we're going to do, and that's what we actually want to write down right here. 2 pi radians is actually equal to, not that we don't have time for this, and I think anyone can help me on this. Just for state a different, oh boy, is that a word? There we go. This gets disconnected. I don't know why. So then pi radians, you saw that I put that up there as 180 degrees. They are equal. All right, now watch what I do here. Okay, this is very simple, and this leads to one of my conversions. So pi radians, we just have to know that's the exact of approximately 3.14. So remembering that pi, 3.14. Watch what I do. If I divide both sides by pi, then pi divided by pi is 1 radian. So this is one of our conversions. This is converting radians to degrees. That's what we're going to use for our conversion factor. So there you go. Radians to degrees, you will multiply something by 180 divided by pi radians. Degrees to radians, flip it, all right? And why this works, these are all equal to 1. These are forms of 1. These are ways, that we can, so we know that we're not changing the value. We're multiplying by a form of 1 because this is something over something that's equal to it. So 3 over 3 is, blah, 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 1. Okay, so change each radian measure to degree measure. Here we go. Look at all these. And not always radians do we have to have the symbol pi in here. We'll get letter C. But letter A does. And then this is another idea that we should hammer down here. So it's 180 degrees over pi radians. This is like dimensional analysis. Let me put that up here. Dimensional. Your science teacher will love me for this. Dimensional analysis. Students are so poor at this, and they don't understand why. Dimensional analysis. Let's say, because really that's all I'm doing when I convert anyway. So dimensional analysis, and this is the idea of fractions equaling 1. Let's change 7 feet per second into miles per hour. Well, it's very simple. It's 7 feet. It actually is a fraction per 1 second is really what 7 feet per second means. The first thing you want to do is change feet to miles. So what is the fraction I can multiply it by that is equal to 1? And it is this one. And this is why I want miles on top, because I want feet to cancel. Never understood why students have a hard time with dimensional analysis. Actually, it's very intuitive, very easy. If you understand fractions, that's the big part. Oh, all the years of students not doing well with fractions. Radians are going to be a problem if you're fractionally challenged. All right. So here's what I mean. This is why feet go on the bottom. The feet cancel. How could we switch that? Really pay attention to how the labels cancel and the labels that end up being left over. So I've already converted feet to miles. We had to do the calculations. And then seconds to hours. Okay, so I got to start with some fractions, like how many seconds are there in a minute? 60 goes on the top because I want seconds to cancel. Why do we make things challenging? I'm talking about students of the past. Hopefully all my students this year will understand this dimensional analysis, and your science teacher will love it then. And then how many minutes are there in an hour? There's 60 minutes in an hour. Very, very simple. I don't care. That makes you mad when I say those things. It should be. You should understand fractions, understand how to cancel things, and make it easy on yourself. Okay, so then you go to the calculator and type this all in. No time for this. You should know how to type this in. This times this, divided by actually 5280, and then you get an answer. So why did I cover that? You should never screw up. Is it 180 over pi or pi over 180 when I convert? Problem is you don't see the word radian. So this is radians because it says so, and now the word radian cancels because the word radian's on the bottom. Right? And I know that's a fraction, 9 pi over 5. So where does the word radian belong? It belongs up the numerator as far as this dimensional analysis is concerned. Oh, I got to do one more thing too. Most of the time radians have a pi in it as well, so you need the pi to cancel. So that's another indication of 180 over pi instead of pi over 180 and converting. Okay, oh boy, sorry for this video. I can't pause it either. 5 goes into what, this is embarrassing. To 18, 36 times 9, holy cow. I just got to go ahead and type that on. The calculator is going to take forever to open, so we'll wait for that. All right, and then this one, of course. Oh, I see a pi. Okay, yeah, you'll get away with it. Okay, the pi's canceled. This one I do know. This ends up being negative 270 degrees. Oh, so I see where this is going. This is one of those special angles that land on the unit circle, and we're going to actually have that coming up here. All right, negative 1 1/4 is negative 5/4. This one, no pi cancels. It's often funny how students cancel the pi, even though there is no pi here. No, this one you just, you go ahead and get this in a decimal. So negative 5/4, negative 5 divided by 4, times 180. Enter, and then it might be fine and good that I'm doing this divided by pi, which is right up here. It's the caret button. Okay, so you get negative 71.6 degrees. Negative 71.6 degrees. Okay, so converting. All right, and then let's look at what we have here. Change each degree measure into radian. Oh, and then there's that unit circle. We're going to go ahead and put radian measures on that now. All right, 80 times. Now this one's times pi over 180. Very simple. The word degrees cancels, and you're left with radians. That's why I did that dimensional analysis real quick. So we should never switch these two. It's common sense what happens there. Oh, I never calculated that last one. You go ahead. I don't know. 8, what does this reduce? 8 goes in 18, 2 goes in, okay, so 80 over 180, the 10s cancel, and then this is 4, no, 2 goes into this 4 times, and then 2 goes into this 9, so it's 4 pi over 9 radians. That's writing it in exact form. Okay, and then I don't think I have to do all these, plus I'm struggling on with my calculations here, don't want to pull the calculator out. So I'll skip to this one, degrees. The zeros cancel as well as the degrees. And I think this is negative 8 pi over 9 degrees. Then you'll find out that these are not anything special. We're going to go to the unit circle now. In our CAT book, they have a blank unit circle. Actually, they don't. In section 3.1, they have the unit circle, and they have alternating between degrees and radians, and they have to fill in the other one. Right? So we know from our previous thing that we had, and I guess I will put these here, and I'll try to color code them. So remember, this was 30 degrees, and then this was 150. And then this was 330. Go ahead and look at your notes. And then this was 210. What you're going to find out is those red ones are all 30, 60, 90s. Notice I'm emphasizing the 30. So the 30-degree angle is the reference angle that you play SOHCAHTOA with. That was our notes today. All right, and then we'll go in green. And then this was 45. The 45 in quadrant 2 was 135. This is what we did today, and then that's why I had these pictures when we actually did SOHCAHTOA. 225 and 315. And then I guess I'll go in blue, even though blue doesn't really show up much different than green. This was 120. This was 240. And then this is 300. Okay, it's the fractionally challenged that are going to, only ones that are going to have trouble with radians. Oh, by the way, 90, 180, 270, 360, oh, and 0. Okay, now, next to these angle measures, I'm going to put the corresponding radian measures. Okay, and that's, I can do it through converting as well, but I also know them. And I know what happens, so please pay attention to this. This is like the most important thing for you to understand. If you're not listening, you're not watching this video. Well, who am I yelling at if you're not watching? But, you know, this conversion and what I already know, hopefully you can get there quick. Okay, fine. 0 radians. 0 degrees is equal to 0 radians, sure. But what did we say a full rotation was? 2 pi. That was our whole basis for our conversions. 2 pi radians equals 360 degrees. You just got to lock it in. The second video talks about that. I think maybe the first one does as well. Comparing it to circumference, and no matter what the size of the radius is, when you take the circumference divided by the radius, you end up getting 6.28 radians. I think I said that right. And then pi radians is over here. Half. Okay, so once I tell you 1 or 2 pi is 1 rotation, half of that is half of 2 pi, which is 1 pi. Right? So get that down. Now the next thing we're going to do is take half of that, just like 180. Half of 180 is 90. Half of pi, oh, that's pi over 2 radians. Okay, so again, understanding what's happening, a different way of expressing angular displacements with radians so that we can use them in real-world questions. Now the problem is that bottom one. Well, I'm going to do this quite a bit. 0 pi over 2, 1 pi over 2, 2 pi over 2, 4 pi over 2. What did I say that I didn't say? 3 pi over 2. I wanted you to say it to yourself during the video. So that's 3 pi over 2 radians, cutting this up into quarters. So now we got those angles taken care of. Now, what we can do, and this is what my CAT students have to do, take these angle measures and convert them into radians. And I should have you do that. You should go ahead and go through a process of converting all of these. I wish I could pause the video and have that happen, but I can't. Right? So 30 goes into 180 6 times. So guess what? This is pi over 6 radians. I'm going to go over to this red one. I'm going to convert 150 to radians by multiplying by that conversion factor, 180 over pi. This becomes 15 over 18 pi, and then that becomes 5 pi over, look at the denominator, 6. I wonder if a pattern's developing with the red angles. 210, I'm not going to do these, so I'm only going to do them for these. Shove the other ones at you here when I do all these convertings. 210, that becomes 21 over 18, the 10s cancel, and then this becomes 7 pi over 6. So all I'm doing is fraction reducing here, guys. The fractionally challenged will be the ones that are like, what's going on? It shouldn't be that bad. And then taking 330 and converting it to radians. 10s cancel. 11 goes into 33 3 times, and 3 goes into 18 6 times. Ooh, 11 pi over 6. What a weird pattern. Well, let's look at some other ones and then see what Mr. Samuelis is getting at. 45 degrees. When I take 45, I hit an into green. 45 and convert it. This goes into this 4 times. 45, 90, yep, 135. So this is pi over 4 radians. This is the corresponding radian measures to these angles, right? And then I'm not going to bore you with these conversions. I just know the answers. When I convert 135 by multiplying 3 or pi over 180, you get 3 pi over 4. 45. When I take 225 and hit it to pi over 180, this becomes 5 pi over 4. And then when I hit this one, multiplying it by pi over 180, this becomes 7 pi over 4. Huh? So 45s end up being over what? Okay, let's move on. And I know you're brand new to the unit circle of the degrees anyway, but everyone I asked today really did a good job with getting our angle measures and doing our trig on it. And then when I take 60 times pi over 180 is really easy. That goes in 3 times. So this is pi over 3. And then this one is 2 pi over 3 when you convert it. This one is 4 pi over 3 when you convert it. And then this one is 5 pi over 3 when you convert it. So there is the corresponding radian measures corresponding to the particular angle measures in degrees. Then I wanted to erase this so my extra stuff is out of the way, so you only see what is important. You know what? And that's the question from the last. Okay. All right. So lock it in. Hopefully you constructed this along with me. Otherwise, you're severely and totally behind. Oh no. Now, and this is what I'm going to end with. And I'm not going to do this. We're not going to do applications. We're only going to do trig. But what's nice about radians is your like area formulas and arc length formulas can change a little bit because radians work really well with actual side measures. So sine of 5 pi over 6. I know we just constructed this, but listen to me. Here's what I'm going to want you to do on this. You're going to create a triangle or create, draw the angle and then create a triangle from it. So 5 pi over 6. I know this is new to you, but please, hopefully you've caught on with the connection here. The over 6s were those red ones. So this is going to be a 30, 60, 90, right? So I converted, and I think already know what the answer is, but this is how you're going to do it. You're always going to compare these angle measures to either pi or 2 pi. That really is the best way, and this is the fractionally challenged that can't handle this, that, when I ask, where's 5 pi over 6, what quadrant? This is what you do. Pi is equal to 6 pi over 6, isn't it? All right, now why did I choose that? Because that's my denominator I'm dealing with. So I'll ask my CAT students the same thing. 6 pi over 6 is pi, so where does 5 pi over 6 have to land? And everyone should answer that this should land in quadrant 2, because 5 pi over 6 is 1 short of 6 pi over 6. Right? And then if you really remember that 5 pi over 6s, anyway, are 30-degree angle measures, then this is exactly what I ended our today's notes with, or Monday's notes. So here we have a 30, 60, 90 in quadrant 2. Right? Going back up to the cheat sheet thing here, 5 pi over 6, right here, 150. Converts to 150 degrees, so yes, that is a 30-degree reference angle right there. Side opposite to 30, 1. Side opposite to 60, root 3. Side opposite to 90, 2. The longer it takes you to memorize that, you're doomed. Oh, this is coordinate trig. That's a negative. That's a coordinate, so it's negative root 3, comma 1. And then I construct the triangle x, y, come back down with the hypotenuse to there. What's sine? Well, with all that being said, sine is so. So after all that, this ended up being a half. No calculator, no siree. All right. So remember what I said. Compare to pi or 2 pi. Erase that. That's pi or 2 pi. Well, pi is 4 pi over 4. Why did I choose that? Look at my darn denominator. So I want to make a comparison. Where does this fall compared to 7 pi over 4? Well, then this is 2 pi. So that's equal to 8 pi over 4. And again, the fractionally challenged. If you can't understand how 2 pi is equal to 8 pi over 4, I cannot help you. I can't. There's nothing I can do at this point if you don't get that. So now, where is 7 pi over 4? Well, don't be cheating and looking at your unit circle. Understand 7 pi over 4 is short of 8 pi over 4, but very close. You are in quadrant 4 with your triangle. Coordinate plane trigonometry with radians. All right. Now, hopefully you saw the pattern of over 4s. It is a 45. Okay, so this does equal 315 degrees if you converted it. But I don't want that. I don't want you converting radians to degrees, then doing your trig. I want you to do what I'm doing here. I want this thought process. I want you to remember that over 4s are 45s. Right? I know that's a quick progression when I was doing this unit circle, but look, the greens, when we were doing our trig with the angle measures in degrees, the green ones were 45, 45, 90. So that implies that pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, or any over 4 angle measure would, as long as it's in fully reduced form, would equal a 45 somewhere in some quadrant. All right. So with all that being said, speeding this up, 45, 45. Side opposite 45 is 1 and 1. Side opposite the 90 is root 2. You're either going to get those memorized or not. Okay. Oh, and then right 1, down 1. do not forget that last part. My CAT students always forget that. Not always, but a lot of times they forget that. What are my actual coordinates to get to this position? And it's 1 right, -1 down. All right, because of a 45, 45, 90 similarity and what we talked about, A root 2. All right, and then this is opposite, adjacent, and hypotenuse. And we'll stick with that. Cosine is adjacent over hypotenuse, which is 1 over root 2, which equals root 2 over 2. Darn, you get another positive because of the sides that I drew from. Of course, the sine of this angle measure, 7 pi over 4, would be -1 over root 2, which would be -root 2 over 2. And you should, as you're doing your homework, yes, this is getting repetitive. You get these same ratios because of what happens with 30, 60, 90 triangles. Okay, 2 pi over 3. This is pi. This is 2 pi. This is 3 pi over 3. You should already know what quadrant this is in. This, by the way, is 6 pi over 3. Can't help you if you don't know fractions and don't know where that came from. Just makes me want to hit my head up against the wall, people not understanding that. But why did I choose this? Because that's an over 3. I want to make a comparison. And I think you've already figured out that 2 pi over 3 would land here. You're not going to have that unit circle in front of you. When we take our next quiz test, we're going to have no calculator on this, and you're going to have to draw this triangle and know that 2 pi over 3 lands in quadrant 2, and I'm showing you how you do that. It'll take some time. This is sometimes one of the harder things, but really could not be. As long as you get these things down, side opposite the 30 is 1, side opposite the 60 is root 3, side opposite the 90 is 2, and there's no excuse for not getting that locked in. Okay, but then again, whoa, you went too fast. 60? How'd you know it was a 60? Well, this will take time, but over 3s, look at the blues. When I converted those, and I only converted this one, I multiplied this by pi over 180. That became 60 pi over 180, and then that reduces to 1 over 3 pi. The same thing would happen with 120 over times pi over 180. You get 2 pi over 3. 240 converted gives you 4 pi over 3. 300, and all of these are 60 degrees away from the nearest x-axis, which is where your reference angle is always at. So the over 3s always end up being a 60, 30, 90, where 60 is the reference angle that's attached to the origin. So triangle must always be drawn like that, and then the last thing is left and then up. Sometimes I put the plus sign just to tell myself that I checked it. The hypotenuse is always positive. The only reason the other sides can be negative is what quadrant you're in. And then what's tangent? Tangent's TOA. So it's root 3 over -1. So it's -root 3. Somebody asked me in class, do we have to do that or do we write decimals? And the direction said exact. So exact implies no calculator, and then it implies that you put it in radical form. Okay, should be done with that. We'll talk more about that Wednesday. Hope you watch this.